Hey everyone, neutron stars are probably among the strangest objects in all of universe, except black holes of course, and as their name suggests, there are a lot of neutrons in them, but their physics is far more exotic than it may appear at first sight. For one, we have no clue of what may lie at their centers. This is about the insane and unknown physics of neutron stars. Neutron stars are remnants of a collapsed star, specifically with a star with a mass of around 8 to 25 solar masses. For stars that are less massive, what you get is a white dwarf, and for more massive stars, you get a black hole. When stars run out of their nuclear fuel and start to collapse under their own weight, a particular kind of quantum effect, applicable only to matter particles, takes over and starts to resist their collapse. Eventually, the cascade of infalling matter rebounds as a supernova, the death of a star. What's left behind is a small but dense, highly magnetic and spinning neutron star. There is no nuclear fusion happening in a neutron star though, so technically they're not really stars. But the stuff happening inside these neutron stars or any other remnant is just as interesting, if not more. The normal mass of a neutron star is around a couple of solar masses, but their size? Tens of kilometers. The insane gravity is such that electrons and protons are merged together in a process called electron capture, forming an increasingly neutron-rich liquid. You may have heard of that most of an atom is empty space. Now think of filling all that empty space with more and more nuclei. This is how you achieve such extreme densities. And it is quite interesting how they counter gravity to resist their further collapse, an outcome of an inherently quantum phenomena. One of the things that is applicable to all these stars and their stellar remnants is that even though we always think of them as highly macroscopic, bulky, non-quantum stuff, none of them would work the way they do without an intricate quantum phenomena. Stars wouldn't shine without quantum tunneling, and these remnants, they wouldn't be stable without quantum mechanics. All matter particles like electrons or neutrons have this property that they cannot occupy the same quantum state, something that's known as the Pauli's exclusion principle. You may have heard of that two electrons in an atom cannot have the same quantum state. Well, it's the same idea. The particles with this property are called fermions, while the other kind of particles like photons that don't have this restriction are called bosons. In the case of white dwarfs, the leftover core holds itself against the pull of gravity because there comes a limit at which electrons cannot be more compressed, and so they start to repel against any further compression. This electron degeneracy pressure, the tendency to not be at the same place, is what counters gravity, sustaining the system. For neutron stars, a similar kind of effect takes place, but because here a lot of these electrons have been captured by protons to form neutrons, the major player is the neutron degeneracy pressure. Though protons and electrons do have their effects as well, but on a smaller scale. The deeper we go inside neutron stars, the more packed these neutrons become, to the extent that there comes a point at which these are forced to arrange themselves in particular structures like cylinders called spaghetti or sheets called lasagna. And I'm not joking. These structures in which these particles exist is actually called the nuclear pasta. The materials that exist here are probably among the strongest that could. Further down, these neutrons reach the state of superfluidity, in which two of these neutrons may combine together to form something that's called a Cooper pair, a kind of bosonic integer spin entity that could flow without any resistance. Also, all of the leftover protons, well, they become superconductive, helping in the star's insane magnetism. Most of these neutron stars are high spinning, they rotate pretty fast, which comes directly from the conservation of angular momentum because, well, the initial star was rotating because the gas cloud from which it formed was spinning. And so, since the size is now reduced so much by conservation of angular momentum, the speed, the rotational velocity, had to go up. Now, these neutron stars, apart from being high spinning, are also highly magnetic. But how do we explain their insane magnetism? Well, this is also kind of coming from a kind of conservation law, the conservation of magnetic flux. The original star had magnetic fields, and now this is compressed into a smaller size. But conservation of magnetic flux, the magnetic density had to go up. Also, there are dynamo effects at play from the superconductive ions inside the neutron stars that also help in their immense magnetism. Now, there are special kinds of neutron stars that have a substantially stronger magnetic field even compared to the normal neutron star, which already has a giant magnetic field. And so these are called magnetas. How do they have such greater values of any field is still an open question, but ideas range from high spinning binaries along with some form of dynamo effects. Coming back to the big mystery, what's in their core? Well, the extreme conditions inside them may lead to the formation of quark-gluon plasma, which is what the universe was filled with in its very early days, just after the Big Bang. There are hyperons that are like baryons with a strange quark that may have also formed, which are generally exotic particles, and so we don't generally observe them. But in such conditions, they might become slightly stable, and so they can form. But the main issue with all of this is that the conditions are so hard to replicate that we don't have it here on Earth. And so we don't really have any observations with respect to what we might see. What we have are predictions coming out of theory. How much of that is actually true, we don't know. But even though we don't really know much about their core compositions, we know that a lot of things that we see around us formed when two of these neutron stars collided. Much of gold, platinum, and uranium is formed that way. Some of the gravitational waves that we've detected came from these neutron star mergers, allowing us to understand their physics in a far better detail, which gave us many insights into the physics of neutron stars. Specifically, how massive could these be? And it is still a bit of a mystery because we don't really have a confirmed number as to how massive could these neutron stars become. I mean, for white dwarfs, we have this reasonably accepted value of around 1.4 solar masses, beyond which a white dwarf would not be able to sustain itself and would collapse. For neutron stars, we do have a number, estimates to how massive the upper limit for neutron star mass, but it's not really as confirmed and it's a lot more uncertain. For one, neutron stars are high spinning objects, and so their spin kind of influences how massive could these be, with high spinning neutron stars being generally able to be more massive than slow spinning ones. But even after accounting for that, there's this mass gap that we see in our observations, which is that when we look for objects in the night sky, we see that there's a gap in observations between the heaviest neutron star and the lightest black hole. So the heaviest neutron star that we've observed is around 2.3 solar masses, and the lightest black hole is around 5 solar masses. In between, there's this range where we haven't found many objects, which is what we need to have like a confirmation of, okay, so this is how massive neutron stars could actually be, and so confirm the predictions and estimates coming out of theory. We first detected neutron stars as pulsars. So these neutron stars are actually objects that emit these high energy jets of radiation from their magnetic poles. And because in most cases their magnetic axis is not aligned with their spin axis, what we see are these pulses, pulsars, forming some of the most accurate clocks in the universe, on par with the ones that we have on Earth. So there is, of course, a lot to explore, and what we've done is just scratching the surface of the intricate physics that plays out inside neutron stars. But that's all that we have for today. Thanks for watching.